Yeah, that's good. So this is the textbook, which is really a very good one, and to some degree, it has the order of the topics that it discusses. They are very well structured. I highly regard as a very good textbook. There is another author, Gilbert Strang, and this is really this is the name of the author, Linear Algebra. And to some, the books of Strang, or Gilbert Strang, he is a professor at MIT, they are really inspirational. Okay, the way that the examples are put in this textbook, the way that, or the material that you learn once you solve the examples in this textbook, they are very great. Between these two textbooks, I like this a lot, but for elementary introduction to the linear algebra, the first textbook is a little better. Okay, so I can strongly suggest to you to acquire both books, and at least you might go over this textbook. But if you want to solve some very good examples, you can also refer to this one, okay, to this Gilbert Strang textbook. Now, if you go over all the exercises at the end of the chapter of the first textbook, it's also good because all the solutions are in the same book. Okay, so which is a good exercise. You try to solve them. If you don't do a very good job, you can look at the answers at the back of the book. There are also some problems who don't have the complete solution, but they just have the answer, which also does help. Okay, so the first one is a really good book, and after I used this one for a couple of semesters, I said, let me choose this one, but I can give this as a secondary reference. Now, this is the general information about the text, how this course is going to be organized, and the next important piece of information is the following. In this course, we have a compulsory midterm exam that will be, we have a final exam. So the midterm exam, it will cover for 35% of your grade. The final exam, it will cover around 45%, and the rest, it is 10% homework and 10% quizzes. Quizzes, they are organized here in the class, and homeworks, there are assignments which will be assigned to you to be done over approximately 1 week ahead. You will be notified that you're going to have a homework. Okay? It can be less, but more or less it's going to be a week notice. So this will be the grading structure. Then after this, I can go over some. So what you can refer to as an important piece of material is the syllabus. Of course, you cannot see it from the camera very clear, but I have to confirm this one, which is that's strange. Is it upside down? Yeah, stop. How is the camera? I know that cameras do left-right inversion, but upside down, it doesn't. Huh? What do you mean, sir? But
text. You need to turn on the other one.
No, is it upside down?
No, it's not upside down.
It is upside down.
Don't look in the projector.
Oh, the projector reverse is upside down? No, it's also here upside. No, it looks good. I'm used to seeing the header a little. Oh, I really was surprised. Let me check this one. No, it looks good. Okay, interesting. Okay, these are printed from an HTML website, not from a PDF, so the header is all shifted, so I was really confused. Okay, so initially we'll start with discussing the matrices, the definition of a matrix, the basic operations such as addition, scalar multiplication, matrix multiplication, and then we'll talk about the elementary row operations. So initially we'll start with, of course, you can see this part. So we're going to define what is a matrix. Okay, so what is a matrix? Then we'll start to do addition, subtraction, operation of two matrices. So matrix is something which we denoted like this: A, M, N, and B, N, K, for example. So we're going to study, and the matrix in this course, we might often denote it like this. Matrices, they are templates of numbers, or mathematical constructs composed of numbers, which are put in a two-dimensional array. Okay, so that's why if a vector is often denoted like this, so this would be like a vector, vector quantities. We're going to do a lot of vector quantities in physics and other fields of engineering. But this one, we're going to denote this one as a matrix. Okay. So you might, in the class, in the homeworks, in the quizzes, you might denote using the same notation, and you might see me also following the same pattern. Okay. Now, these are, so we're going to start matrices, defining them, addition, subtraction, then multiplication. The multiplication, we're going to do multiplication by a scalar, which means that by just a number, and multiplication by another matrix. So these matrices, they are arrays of numbers, and we can do these operations. Then the next topic that we're going to do is row operations. Okay, so row operations, they are very important. Yes, come on. We're almost okay. We should have it. Then, after studying the row operations, we're going to work on solving linear systems of equations. There's no chair. There's no chair. Problem in chair here, no. Also, a bit situation. Dacă avem să facem și un care când el și iar și să dă șumiți pe aquí. И плюс аз съм спасил бил. Ai къде аз да ти?
Dobro vamos
Добре persone.
Să fie pâsnă.
Ja, sure. Kjo është një ide që përsen kohën. Okay. Then the next step is we're going to study linear systems, solving linear systems. So what does solving mean? Solving means that it's the same thing like you have an equation. An equation is something where one construct or something is unknown. Okay, so actually this is something very. I mean, you chose to study electronics and digital communication engineering, and often it is this is just a small parenthesis. Okay, what is an equation? An equation is anything which is something like this: 3x is equal to 9. Okay, you have to find x. That's it, right? So, and here you might derive that x is equal to 3, because if you substitute this 3 here, the identity is confirmed. Okay, so it ends up being true. At the same time, we can have another type of equation. So this is the first type of equation. That's good. I mean, we might have seen equations like this a lot. The second type of equation, it could be the following. We can have, for example, dy over dt is equal to 4y. Okay? This is another equation, which means that what is the unknown here? The unknown here, we have a variable, we call it y, which is apparently it's a function of time, and we are told that that y as a function of time, it varies, it changes like this. Then what is the solution of this equation? The solution of this equation is going to be something like this. Y is equal to e to the power 4t times another constant. So let me write the constant here. I could have written in the front. So this is the solution. And then the question is that, okay, can we confirm if this is true? I mean, is this really the solution of this one? So what one has to do, we have to substitute this value of y into this equation. If we try that, we can see, for example, what is the derivative of y with respect to time. I'm pretty sure that in calculus you are going to learn that the derivative of this function, the derivative of e to the power 4t, is going to be 4 times the same functions. So we end up by taking the derivative here, we get 4y is equal to 4y. So it might be very easy. In a couple of weeks, you are going to learn this, see this again in calculus. You might confirm that this is really the solution of these equations. That's good. Now, can you get more different types of equation? Another type of equation is the following. If, for example, we can have the second derivative of y with respect to x squared, and this would be equal to some constant k times the second derivative of this function y with respect to time. So this is also I mean, these equations that we just see now, these are called differential equations because you're calculating derivative. This is d. Let's write this d. Derivative, second derivative. It's better looking if we write this other one, which is called a partial derivative, but don't worry about it. Let's assume, so the way to read that one is that the second derivative of y with respect to x is equal to some constant k times the second derivative of y with respect to time. That's good. So what do we understand from here? Apparently, we have a variable which depends y, it depends on x and time, and we have to figure out the solution, right? Now, this is called a wave equation. You chose to study electronics engineering, you're going to solve a lot of wave equations, differential equations. They are very easy, but for the moment, we're just trying to kind of remind ourselves that, okay, whenever we have an equation, we have to find out some expression. In this case, the expression that is unknown to us, it might be a constant, which might end up like this. It might be also a variable which depends on another variable, which in principle, this would also be written as y is equal to y as a function of time. Now, it's not that I wrote this out of nowhere. I will make also a relationship of these points with the linear algebra. But so here, it looks like y, it's a function that depends only on time. But here, y apparently depends on time and another spatial variable. Spatial parameter, okay? Not time, so it depends on x, which is also measured by meters most of the time. So these are the unknowns. Now, when we go to linear algebra, in 2 or 3 weeks, we're going to start to study the linear systems and we have to solve them. And whenever we say we solve, we need to find the unknown. These types of linear systems, they are going to be formulated like this. We can have a matrix A multiplied by some unknown vector x, and this would be equal to another vector b. Okay? So that type of equation, it looks like very close to being equivalent to this. Okay? So then a simplistic approach of how to find x over there, it could be the following, which is not always true, which is x could be equal to b divided by a, if we divide both sides of the equation. But this is partially questionable because division by a matrix, it is not defined. Of course, we left it like that, questionable, don't take it as a proof for the future weeks. Now, when you say solving linear systems, so here, this was an equation, but now here, this is an operator, okay? So what this part means, for example, this d over dt of a variable y, this in itself is a function. It's an operator, and the beautiful aspect of linear algebra, which makes it very impressive, is that this whole operator, this can be equivalent, this is not equal, but we can write this one like a matrix representation of the y, which means that apparently this operator, it can be represented by a matrix. At the same time, this second order derivative, this can also be represented by another matrix. For example, here we can have the second derivative with respect to time of y. This can be represented as another matrix B. So linear algebra, it is a very, or at least the mathematical apparatus. I often believe that using the keyword of mathematical construct is very useful because it can help us to solve any type of the most complex possible problems. There are several programming languages which you might be aware already, or that we are going to hear during your 3 years of study program here, or new programming languages that will come up that don't exist right now, but in 2 years they might come up as new programming languages, and then you might have to learn them while you are in the 3rd year. 2 years ago, PyTorch is a package which was not existent. It just was showing up. People were developing, but now it's out there. So students that started the bachelor study program 3 years ago, this PyTorch did not exist, now it exists. They have to learn it, use it. Similarly, like many different programming languages, there is a programming language which is called, it's a high-level programming language, which is MATLAB. MATLAB, it's a good one. You can download this one actually using the EPOKA institutional email. You can go to the MATLAB website and download it. It's a good programming language. This is equivalent to a free version, which you might find this often, which is Octave. But the purpose is not here just to talk about this programming language, but this MATLAB, this means matrix laboratory, which means that all the algorithms that run into this programming language, they are written in the computation of matrices. So one can solve differential equations, which are the two differential equations at the bottom, using matrix principles. So this linear algebra is really a very good tool to use. And once you do, you might find two different approaches of how to solve a problem. Always, if you use the principles of linear algebra, it will become much simpler. Okay, so we are learning linear algebra to solve very complex systems or very complex problems by using very elegant approaches. So differential equations is a very, I mean, so to say, so it has some level of difficulty, but using linear algebra in differential equations, it will make them more easier. So again, when we say that we have to solve linear systems of equations, any linear system of equations or unknowns, it looks like this. Okay, so even a derivative, even this equation, this one, it can be formulated like this. So often, expressions that we may be used to seeing this quite a few times, these expressions can be from this three, it can stand for a matrix, this time it can be a vector or another matrix. And our task, it will be to find the unknown, in this case, find x. So when we say linear systems of equations, right away, we are going to work mostly with numbers, but I want to remind you at this stage that these can also be generalized for more complex problems, and it's not, of course, we are going to talk about these in detail later again, but I just want also to add some more basic information that you might be aware at this stage. Okay, so then after these principles, we are going to study up. So this can be 1, 2, 3, 4. Then we are going to talk about the properties of matrix parameters. Okay, this is such as determinant, what else? Inverse of a matrix. And the matrices, they are really, maybe I like to write this word, so they are mathematical constants. And these mathematical constructs, they have several parameters, and these we can, like a determinant, it's a parameter which is associated with a matrix. But the properties are very perplexing. I mean, they are beautiful. They have very, once you work with them, now you have to go and publish it. Yeah. Okay, so as we're saying, this mathematical constructs, they have important parameters, which we're going to call these determinants. And after these determinants, we're going to talk about the vector spaces. Vector spaces is an interesting, it's a very important concept because it gives you a full understanding of vectors in a space, or even considering the dimensionality of a space. Dimensionality of space, and this is where the most tricky and the most important beauty of linear algebra. It starts to show itself, and after this point we are going to discuss about the basis. The basis. Once we learn basis, we're going to study the change of basis. And the change of basis, in principle, they are, so what the basis is for example, so far, with basic mathematics that we have studied, or that we have taken in the previous education years, we may have heard about the orthogonal Cartesian coordinate system. Orthogonal Cartesian coordinate system, the orthogonal stands for this perpendicular, or conjugate, or reciprocal. So there are several synonyms of this keyword here, which they are not 100% synonyms. They have some. They cover some different aspects of the understanding of space. But this orthogonal Cartesian coordinate system is a system where we have often denoted this like x and y, right? Now, this is a basis, which means that any point in this space, if it is here in the first quadrant, let's call this one, we call this the first quadrant, where x is larger than 0 and y is larger than 0. This would be the second quadrant, okay? In the second quadrant, x is smaller than 0 and y is larger than 0. So this is, let's say, the Cartesian coordinate system. This is how we call it. And our basis in this case, it is going to be, for example, the x and y. We're going to learn in this course, at least first, we're going to learn how we can change the basis from xy to a new basis that can be, for example, zw. And having another basis like zw, it will be equivalent to represent at any point here. So this can be our z, and this can be our w. So we can have these two double line orientations, but they can also be used to describe points in space. Then, immediately after this basis, we're going to discuss about the eigenvalues. Or let me call it this way, eigenvalue equation. So again, what was an equation? An equation was where it was a construct where something is unknown, and we need to find this unknown. After the eigenvalue equation, we're going to discuss the most important topic. So actually, we learned linear algebra just for one thing. So we're doing all of these little tricks just to do this. This is what linear algebra is done for. So this is the purpose of linear algebra. So everything is like to prepare us to understand how a system can be diagonalized. Okay, and this in this case, the diagonalization. First of all, we're going to see the definition of being diagonal. We can have a matrix, a mathematical construct which is composed of numbers, and then we need to diagonalize it. We're going to talk about the diagonal matrices. And then, after we learn these, we'll see that many matrices, they can be diagonalized using eigenvalues. Now, this diagonalization, this can be done using eigenvalues, and these eigenvalues, they can be used only on square matrices. We're going to see the definition of this square matrix, but in case the matrix is not square, we don't stop there, because we have developed very useful, wonderful tools to diagonalize a matrix using singular values, and these we're going to study again later on, singular values. Now, this information, you can find this in the syllabus, so if you go and click to in your course curriculum, I can show it to you because we are here, which means that your complete study program, you can follow it from the website of our department, that your study program is part of. So you can go here, or for example, this specific course, if this is the course structure, linear algebra stands somewhere like this. So all this content that we just went over, this will be covered over the 14-week time period. Here in the 8th week, you are expecting a midterm exam. The course evaluation, you can find it here in terms of the percentage of the homework, midterm quizzes, and final exam. So this is the information I just wanted to go over, but I want to remind you once again that the whole purpose of linear algebra is diagonalization. And diagonalization, it's in electronics engineering, it is very essential, it is very important. That's why we're going to focus as much as possible in the key elements that are most useful to you. Do you have any questions so far? So this was linear algebra. This is how we plan to do this course, as we have done, as we always do it. Of course, here linear algebra, it's a field, it's a branch of mathematics. It has a lot of proof aspects. There are many elements which might need to prove one thing or another. This type of proof, we're not going to do a lot of these proofs, but whenever there is some intuitive catch, we might present it here in the class. What we want you to understand is that it might be very beneficial for you if you just focus on the application, okay, or how we solve a certain problem. And we'll always try to offer the nice problems, nice, well-defined problems that you will have to solve. And whenever you have something which is kind of not very clear, you can always ask, where do we use this? This is a good question. Sometimes you say, why do I need derivatives? I mean, don't ask this, because it's very straightforward, it's very trivial, but you can ask in linear algebra. And but please don't forget this word. So you might, between forgetting the name of the course or this keyword, you might forget linear algebra. Just remember this. It's more essential. It's much more important. The diagonalization. So you can say that, okay, this professor that taught us linear algebra, he said that this was the most important aspect. Many people might agree with this. Okay, so now let's continue immediately with some notes I put together. And as I said, we're not going to see slides in this course a lot, or maybe not at all. But I just put something together to help us. Okay, so let's continue. We said that we're going to do linear algebra. Everything is good, but in the fundamental, so this linear algebra, the easiest thing that you might have observed so far, they can be vectors. So what is a matrix? As you can see it also from there, a matrix, it's an array of numbers which has m rows and n columns. Okay, so this is how a matrix can be defined. For example, here in the board we have a matrix which is the first matrix. It is 2 by 3. The matrix 2 by 3. It is one that has 2 rows and 3 columns. So 2 rows, for example, the first one is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is the first, let's say the first matrix that you see over there on the slide. And yeah, I could have shared my monitor, so this will be over there, but you are here, so you can see this. Okay. Let's see how this will end up. Okay, so this is one matrix. Then we have another matrix, which is 3 rows, 1 column, which is this 1, 2, 3. In this case, the matrix B can be 3 by 1, which would be equal to 1, 2, 3. So we can denote here 2 by 3, 3 by 1. Or another matrix, it can be the other one shown on the slide. Now, in order to count these elements, we can always ask, for example, what is A 3? No, what is A 2 1? A 2 1 is A in the second row, first column, so this would be equal to 4. For A 2 2. A22 is going to be A in the second row and the second column. So it will be the intersection of these two. Second row, second column. This would be equal to 5. If we talk about B31, this would be third row, first column. This is equal to 3. Okay, so this is how we're going to identify the location of a number in this array of numbers, okay, in these matrices. Yes. Then we can define out of these matrices. So this is again the general definition of a matrix. So any matrix, it can also be denoted like this. So A Mn, which in this case can be A23. This can also be denoted as Aij. Okay, Aij. We are somehow denoting all the elements. So in fact, this is also, we can also call this one A21. Okay, this can also be called A22, which is an element with this address. Okay, this is how we denote it. And here in this case, I is going to be a number from 1 to 2, and J is a number from 1 to 3. Okay, so this is how these can be denoted. And we can use, let me think for a moment, yeah. So Aij is the entry in the ith row and the entry in the jth column. Now the first, among many definitions, we can talk about initially about, well, let's talk about square matrices. A square matrix is a matrix where M is equal to N. Okay, so once the number of rows is equal to the number of columns, it will be a matrix. And by the way, this is a matrix, right? This is also a matrix, but this looks also like a vector. So this B, we can also write it like this, like it's a vector. This is also a matrix. This is a general form in terms of the vector notation. A square matrix is a matrix that looks like this. For example, a matrix C, it's a matrix which is 1 minus 1, 0, 2 minus 7, 1, minus 5, 4, 3. So this is a square matrix because this is 3 rows, 3 columns. Okay. Now the question is, can we have a matrix that looks like this? D, it can be equal to 1, minus 1, 0, 2, minus 7, 1, minus 5, 4. I mean, is it possible to have a matrix like this, whose shape? Any answer? Any idea? No, right? So this cannot happen. We cannot come up a matrix like this. So there are square constructs, not square, sorry. There are two-dimensional structures, but you don't have losses like this. Okay, it can be 3 by 3, 4 by 4, 4 by 7, etc. So this is never possible, but a square matrix, it looks like this. Now we can, after the square matrices, define diagonal matrices. Diagonal matrices is going to be a matrix. We can denote this with a D, which can be whose all the entries which are not on the diagonal, they are equal to 0. For example, here we can have 1, 0, 0, 0, minus 7, 0, minus 5, sorry, I'm trying to mimic this, 0, 3. So this is a diagonal matrix because all the elements, all the off diagonal terms, they are 0. Okay, so only the diagonal terms survive, and this I have to do something better. For example, a diagonal matrix, it's a matrix or equivalent to Aij equal to 0 once I is different from j. Let me think for a moment. Yes. Okay. So this is a diagonal matrix, which means that if the matrix D it is 3 by 3, then we consider what is A3, 2. If these two numbers are different from each other, then this means that this should be equal to 0, right? What about A22? This A22, this does not have to be 0, but this can be 0. We can have A11, this can be 7. We can have A12. The moment these are different, we define it as 0 because this is a definition of this diagonal matrix. Now, two matrices, the other definition is the following. Two matrices are equal if they are the same size and if the corresponding entries are equal. So matrix, when are two matrices equal to each other? A is equal to matrix B if Aij is equal to Bij. Okay? With this one, this means that every element of A should be equal to every element in B. For example, let's have here another matrix. Let's call this one matrix E. And matrix E, we can write this one 1 minus 1, 0, 1 minus 1, 0, 2 minus 7, 1, 2 minus 7, 1, minus 5, 4, 3, minus 5, 4, 3. So then the question is whether the matrix C is equal to matrix C. We just can check them one by one. If the first element here is equal to the first element here, or if this second row, third column is equal to the second row, third column. If we check them all one by one like this, then we may confirm that these two matrices are equal to each other. So these are a couple of matrices of different order. The first one, since that you can see on the slide, one is called the square matrix of order n. The other matrix, which is 3 by 3, it is a square matrix of order 3. Now, the diagonal terms here, they're simply going to be A11, A22, and A33. So, if we have large matrices, we can sub-partition those, which means that we can separate them into smaller pieces. Do you have any question for what we're doing so far? Yes?
Are the numbers on random or are they like...
The numbers?
Are random?
Well, for certain, right now they are random, but for whenever we have a problem, they are going to represent numbers that are defined before. So they are not, let's say, they are not random. Okay. For example, when we are going to solve systems of linear equations, these numbers will represent certain relationship between 2 or 3 variables, 2 or more variables. Okay. Any other question? Okay.